Hi, I'm Saman, a PhD student at Monash University, and today I'm pleased to present our recent work entitled with Vehicle Dynamics in Pickup and Delivery Problems Using Electric Vehicles, co-authored by Guido Tack and Daniel Harabor from Monash University and Philip Kilby from CSIRO Data 61. The pickup and delivery problem PDP is a well-studied topic in constraint programming and operations research. PDP is a point-to-point transport problem where a fleet of vehicles needs to serve requests for moving loads or passengers between a set of pickup and delivery points, while respecting essential constraints such as vehicle capacity. The solution to the PDP is a set of routes, one route per vehicle, that satisfies both problem objectives and transport constraints such as time windows. If electric vehicles or EVs are operated in the transport system, we also need to track their energy level and plan charging detours if necessary to fulfill the transport request. EVs offer higher energy efficiencies. However, limited energy capacity and also the lengthy charging process in EVs may require substantially different routing decisions compared to conventional vehicles. So what are the routing challenges? The first challenge is planning charging detours if the available energy of the EV is not enough to complete the trip. And if this is the case, charging detours would increase the total trip time. On the other hand, if we need to have fewer charging detours, we might need to choose energy efficient path rather than shortest path. But again, energy efficient paths are normally longer than shortest path. That means we always have a trade-off between energy and time in routing problems for EVs. There are also some challenges in path planning for EVs. We need to have a relatively accurate estimates on energy requirements of point-to-point path to carefully track the EV's energy level and possibly add charging detours. To tackle this challenge, we need to appropriately incorporate the main parameters of vehicle dynamics into energy models. To better explain to what extent vehicle dynamics can affect the energy consumption in EVs, we solved a PDP with 14 transport demands as depicted in figure in right. So the trip was planned using the simple fixed rate energy consumption of an EV with 16 kilowatt hour battery capacity and 100% initial energy level. Based on the energy plot in the left side, the trip seems feasible as its required energy is less than 16 kilowatt hour, the red line. But as you can see in the left plot in blue, the trip would require more energy when passenger weights are incorporated in energy model, and even more when the ground slope is also added into the energy calculation. This means the last two pickups are infeasible with more accurate energy models, and the trip might be infeasible in reality. But how can we achieve more accurate energy models for EVs in the PDP? Well, we first need to identify the main parameters in vehicle dynamics that affect the energy requirement of links in the underlying graph. As the exact calculation of the link's energy requirement in the PDP setting is a difficult task and requires online solving of complex differential equations, we built our energy models based on three main parameters in vehicle dynamics that change with transport requests and transport location. These parameters are gradient, extra mass, and changes in vehicle speed. In the second step, we need to train energy models. The plot in the right side shows changes in energy efficiency with different road gradients and extra mass for a sample EV. To obtain this plot, we use Advanced Vehicle Simulator evaluated under the realistic drive cycle called WLTP shown in the left side. We see a nonlinear relationship between energy efficiency and road gradient. In addition, the plot shows that increasing vehicle mass can either increase or decrease energy efficiency depending on the gradient. Now, based on the relationship obtained from our engineering simulation, we can learn an energy model that takes all the parameters into account. This model is named the full energy model. In this model, M is extra mass, G is road gradient, and D is the actual distance of the link. To incorporate a speed, we learn a separate model for each speed profile. That means the constant energy coefficients alpha and beta are different in driving patterns. This table shows the range of the coefficients learned for the test EV of this study using the speed profiles of the WLTP cycle. So given our full energy model with all parameters considered, we can now derive 6 energy models that take parameters of vehicle dynamics into account to varying degrees. Our base model EB just considers the fixed rate consumption via beta 3. If we want to add mass into this model, we then have one more term including parameter m and alpha 3. Similarly, for models with gradient consideration, we have two relations depending on the availability of extra mass. Finally, to incorporate speed, we just replace constant coefficients alpha and beta with pattern dependent coefficients alpha I and beta I to obtain the last pair of models, including our accurate energy model. Now it's time to design a PDP model. So the PDP model for EV should respect the correlations between energy matters in EVs and routing constraints in the PDP. Although mixed integer programming MIP is a traditional modeling approach in routing problems, in this study we use CP to design and develop our PDP model. We choose CP because it provides a greater degree of flexibility in the way our nonlinear energy constraints are handled. For this purpose, we develop our energy-based PDP model in Minizink. We define each possible location in our model to be a node with at most one status from pickup, drop-off, depot, or charger. For the CP model, we use the successor representation to encode the EV strip. For example, for the simple trip planned in the right side, we can execute the full trip by sequentially looking up each node's successor to obtain the sequence 1, 3, 2, 5, and 1. Node 4 is a charger node and is not part of the trip. I now briefly explain some of the main PDP constraints using the successor representation. The first constraint is tracking travel time for all non-charger nodes on the trip. So given node I as the current node, the time we arrive at its successor node, node J, must be larger than the time at node I plus service time plus travel time delta T. The next constraint ensures that the arrival time at pickup nodes is within the time limit or the time window. So we also set a limit on the drop-off time of each transport request. That is, the total time each transport request spends in the EV is at most lambda times longer than its direct route. For our last PDP constraint, we track the number of passengers at each successor node. For this constraint, delta U indicates the utilization change at the successor node, and the values in the delta U array are positive at pickup nodes, negative at drop-off nodes, and 0 at other nodes. Energy constraints. For every depot node, the available energy of the EV when it arrives at its successor node is determined using the initial energy of the EV. Delta E is a three-dimensional energy array. As you see, the third dimension is the vehicle utilization. In other words, delta E represents the energy requirement of traversing the path between location I and its successor J with K passengers in the electric vehicle. Similarly, for demand nodes, we can track the energy consumption in point-to-point trips using this constraint. The difference between this constraint and the constraint above is that the arrival energy at demand node I can be some valid energy values between 0 and capital E, where capital E is the energy capacity of the EV. I now explain charging constraints. Depending on the required energy and also the technology used at charging points, charging times may vary from a few minutes to several hours. A common method to model this charging component is establishing a linear relationship between energy and time. However, as EV chargers can adapt their power with the battery's remaining energy, and we have a slower charging rate in higher energy levels, linear charging models may not be able to correctly reflect the actual charging time needed for a specific amount of energy. So to model nonlinear charging profiles in our CP model, we map each profile into an array indexed by time. In this model, E star represents the amount of energy charged in a fully discharged battery after spending tau units of time in the charger node. So tau acts as a charging time offset here, and we can determine and lock in this offset based on the arrival energy EI. Given E star as the energy of the EV after visiting a charging node, now we can set a constraint on the energy of the EV when it arrives at a successor node via a charging node. So this constraint accounts for the energy consumption of point-to-point trips from charging nodes after spending TC time in them. So we finally define the lower arrival time to successor nodes via charging nodes using this constraint. So this constraint ensures that the charging time TC is incorporated in the trip time, along with point-to-point travel time and service time. We can also set lower and upper bounds on the charging time. So this additional constraint enforces that discharging in charging stations is not allowed, as the charging time is always non-negative. Also for the upper bound, we have TC as the maximum charging time or time needed to get charged from 0 to 100%. As an extra constraint, we use the global CP constraint subcircuit to create a set of circuits or trips. Since visiting all charging points is not necessary, this constraint allows us to also plan trips without charging visits. For example, among two chargers here, we can make a circuit with just one of them. Finally, the objective is minimizing the total driving time and charging time. I now explain experimental results for the PDP model of this study. Benchmark setup. As none of the existing benchmark cases was complete enough to be used in our complete energy-based PDP model, we designed a set of realistic instances with all the required energy measures. We used the GPS traces from Uber ride-sharing dataset to extract random trips. The data file includes the GPS logs of more than 20,000 ride-sharing trips in San Francisco over 1 week. For the underlying graph, we extract the San Francisco road network from OpenStreetMap and enrich the graph edges of the road network with elevation and speed data using online APIs. For the test EV of this study, we use an advanced open source EV simulator to learn our energy models and energy coefficients. We also picked 5 charger locations in the map, 3 of them normal and 2 fast chargers. All EVs start their trip with 100% initial energy, and we assume passengers' weight to be 75 kilograms. For the instances, to be able to solve them to optimality, we keep the number of transport requests small. We generate 10 to 20 random trip requests with up to 2 vehicles. Pickup time windows for all passengers is 15 minutes, and the detour factor is also considered 50%. Finally, for the energy and time arrays, we examine 2 scenarios. In the first scenario, as our base approach, we consider all point-to-point path in our problem to be shortest path. For the second scenario, we evaluate our instances with energy optimum point-to-point path. This extra set of point-to-point path allows us to better explore the trade-off between energy and time. We developed and evaluated our model in Minisync using the CP solver Chuft as the backend optimizer. To appropriately measure the importance of vehicle dynamic parameters, we solve all instances to optimality. From the solving point of view, we evaluated our CP model against some of the MIP solvers in Minisync, including Ruby, but we found almost all of them slower over the instances. We also observed that handling charger nodes is the main solving challenge, as the time EVs can spend at charger points can be as long as 5 hours in normal chargers. As an example, by removing the normal slow chargers from the list of stops, we could solve the instances much faster, usually in less than 5 minutes. In addition, as we expected, the problem gets much more challenging for the solver with increased number of passengers or, transport requests and vehicles. Last but not least, we did not notice a major difference in the runtime of the models with mass consideration. In fact, models without mass consideration were solved slightly faster. So comparing the results for each instance based on 6 different energy models, we can see some meaningful differences. Here we can see the results for 2 sample instances. First, um, routes may vary up to 20% if we do not opt for the basic energy model in point-to-point energy calculations. The basic energy model is EB, and the most accurate energy model is EMGV, the one that has all the parameters in it. The second observation is that gradient can have more impact on the energy consumption of trips than mass. This is because we see larger energy values for models with gradient. Third, adding a speed profiles into energy calculation further increases the energy estimates of the trips. The main reason is that there are generally more lower speed links on inner city trips than other speed profiles, and lower speed links require more energy than medium or high speed profiles. Finally, we can see that in almost all instances, fast chargers are preferred. The likely reason for this choice is our objective to minimize the total travel time, including charging time. For the instances evaluated under scenario 1 or shortest point-to-point path, we can see that in all cases, the energy consumption and total travel time of tours increases when more accurate energy models are considered for our energy array. We can also see that charging visits might be added to the trips when more accurate models are being used. Even in some cases, charging detours are planned only for the complete energy model. This means routes planned based on less accurate energy models can potentially be infeasible. And even if a charging detour is planned in all models, we can see more accurate models require longer charging visits. This means that having a charging visit in our plan does not necessarily guarantee the feasibility of the trips. Now, comparing the results of 2 scenarios side by side, energy optimum path against a shortest path, we can see that trips with energy optimum path are generally longer than trips planned by shortest path. In addition, as the underlying paths are energy efficient, they contribute to lower energy consumption in more accurate energy models. We can also see energy efficient paths contribute to shorter and less charging visits. As an example, in this case, we can see that by selecting energy optimum path instead of a conventional shortest path, not only no charging detour is needed, also the total trip time could be shorter. Finally, our last observation is that energy optimum paths are also better in terms of energy underestimation, as their energy error is generally less than that of the shortest path. This research investigates the importance of vehicle dynamics in the pickup and delivery problem with electric vehicles. I highlight these points in summary. We noticed that the energy estimates of the trips might be up to 15% less than their actual energy requirement if we ignore parameters in vehicle dynamics. Among the parameters, we see that gradient and speed can make greater impact on energy consumption than extra mass. Although adding mass or number of passengers increases the PDP model complexity, ignoring mass can lead to infeasible trips in some critical cases. In addition, choosing energy optimum path instead of a traditional shortest path would contribute to energy efficient but longer trips. And finally, energy efficient paths offer trips with better energy efficiency that require less or shorter charging visits. Future work could look at integrating the energy models of this study with other real-world routing problems for EVs. And for PDP, Interesting direction is developing appropriate heuristics for our complete energy-based model, as adding math to the calculation increases the complexity and runtime. Thank you for your attention.